Yeah, I forgot my computer, so I had to use my backup. Okay. So we're going to attack with the nucleophile addition first, of course. The electrons that are in the delocalized pi bond will move up onto the oxygen. That's that tetrahedral intermediate, of course. It comes back down and causes the leaving group to leave. Once the leaving group is left, you'll be left with the carbonyl. And so you'll again get another attack on that carbon right there. That's going to give you your alkoxide intermediate. That one now is going to require an acid workup, right? Because all you have available right now is the hydride. And so that's the acid workup part. That both neutralizes your excess hydride, if you have any excess hydride, and finishes this reaction to give you the alcohol. In this case, a primary alcohol here. Anybody have any questions? And so one of the questions I have here, if you have that group right there, can that ever be a secondary alcohol? Tertiary? Anything but a primary alcohol? No, it can never be anything else, right? Because it always has 3 bonds on it that are not carbon. So, okay. So this right here is the hydride reductions for various different acid derivatives. Again, these are the carboxylic acid derivatives. This is the one we were just looking at, which is the acid chloride. But you can do the same sort of reaction, of course, for the acid anhydride, esters. Carboxylic acid doesn't have any reaction usually. And that's because you'd have to lose this hydroxide here, right? And so if you do this hydroxide here, that's going to be less stable, okay? It's too powerful of a base, and so you typically don't get any reaction at all for the sodium borohydride. This right here is your amide. Again, that would make that negative nitrogen group, right? That's a very good base. It's a very good nucleophile. And so this one also doesn't do a reaction. Okay? Because then you have the hydride competing with that negatively charged amide that left. Yeah. Right here, we can see again the acid chloride with lithium aluminum hydride. Again, we see the same sort of reaction pattern, except lithium aluminum hydride is actually a better hydride source. So it becomes more competitive, more reactive, and it can outcompete, outreact the hydroxide and negatively charged amide. Okay? And that's where you're seeing the big difference. Those can react to these ones here. Okay? So let's say that you had something like a amino acid set and you wanted to break an amide, and you don't care if you break the carboxylic acid, which one would you use? Oh my God, I'm expecting you to know stuff. You'd use this one over here, right? Lithium aluminum hydride. What if you wanted to get rid of the carboxylic acid? You have this cool protein, but and it can block this, it can kill this bacteria or virus that you're looking at. You want to kill, but the damn thing has an enzyme that will chop up basically any protein, starting at the carboxylic acid. Can you get rid of a carboxylic acid without getting rid of the amide in these reactions here? We don't have anything there, do we? No. What you could do, though, is set up a reaction that can react the carboxylic acid to one of these other groups. For example, it's not that hard to get it to an acid anhydride. If you get it to an acid anhydride, you can then target it without targeting the amides, can't you? Okay? And that's the sort of games you can play, actually. That's actually a real-life example, by the way, of how you can actually modify enzymes and polypeptides so that they become undigestible and stick around and will keep doing their function over and over and over. Okay? And you can actually then kill viruses and bacteria and microbes with that. Yeah. So, interesting little side note to that. I know. It's like this stuff actually has real-world applications. All right. You never thought it did you? Okay, so here we have our selectivity. Again, we see some selectivity for this. So the ketones, for example, are going to be selectively reduced relative to your esters. So right here we have the ester, here we have the ketone, sodium borohydride. And what you'll notice is you get 90% of this yield without reacting your ester right there. And so you can specifically target the ketone, leaving the ester behind. Okay. This stuff has a lot of implications, which I can't go all into. It would just take too much time. But understand, for example, if you knew you could target it this, and this is where it gets targeted to break down by an enzyme, and this is like an antibiotic, then you could target a specific functional group, get rid of it, and then it can no longer fit into the binding site, no longer be broken down, right? Alternatively, you can do the reverse. You can target something so it is broken down, or it changes the pathway it goes into, okay? By changing functional groups and shapes, right? Okay, so this is going to reduce our esters very slowly, and it does not reduce the amides at all. And so what you can see is that as long as you don't just leave it sitting there in the reaction conditions for hours and hours, as long as you work it up in a relatively timely manner, you can selectively reduce down this ketone here. This is actually a reflection of resonance stabilization, by the way, because this structure right here has a lone pair right there, right? That can get pulled into that double bond. And so that's actually resonance stabilized. Anybody that is late, remind to come up at the end of class, and I'll get you your clicker. Okay, so this is actually the problem we just did, isn't it? Oh my goodness. And notice quite a few of you didn't actually need this problem or the material in front of it to do it, did you? So right here we have an ester. Right here we have a nice little ether, right? And over here we have an acid. Carboxylic acid derivative, in this case, the acid chloride right here. Which group is the reactive one? That acid chloride is the most reactive, isn't it? Yeah. Ester is less reactive, and ethers are usually a bit less reactive than that. And so right here we have something that would be a hydride source, right? Okay. This is the relatively weak hydride source. That's the sodium borohydride. Okay. And then we have ethanol here, which is our second condition workup. That's going to provide us our H pluses, right? Okay. And so what are we going to get for our major product then? Okay. So will we have a chloride on that major product? It's going to leave, right? That'll be the first thing I'll leave. Okay. Carbonyl here. Is that going to be a carbonyl still? Go to the alcohol one. How about these groups? Does this mess with these groups? No. Now, if you left it long enough, could you mess with those groups? Yeah. So this slowly hydrolyzes, right? So this only, again, will be worked on very, very slowly. So if you left it long enough, yes, it will digest that, and you'll have that gone. And this will go to the alcohol as well. But it takes a long time compared to all these others, so you really have to just let it go. Okay, very good. And that right there is the answer, of course. That's the same problem we did at the beginning, by the way, in case anybody was wondering. Because you already knew the material. We're just working out like the specifics, right? How long does it take to hydrolyze this? Which one will happen first? Okay, so this is your carboxylate anion. It's going to be highly resonance stabilized, and so you won't get any further reaction. So if you put this in with a hydride source like this is an acid, and so what you'll do first is the acid-base reaction, right? And you'll get H2 gas, which will evolve off. That makes this an irreversible reaction, and so you're left with carboxylate anion. And at that point right there, we have a negative charge. It's resonance stabilized. There's no way to go forward with this hydride reaction, is there? Yeah. And so we would be stuck. Okay, we wouldn't get the next part of that reaction if you were trying to do that. So remember that hydrides are not only good nucleophiles, but they're also quite powerful bases, aren't they? Especially with the fact that they always make hydrogen gas, and so it always escapes and it almost always becomes irreversible. It's very, very difficult to keep the hydrogen gas involved in the reaction. So anything that is an acid is going to be worked on extremely slowly, if at all. Okay? Anything that's actually going to act as an acid and give a H+, donate an H+, into this reaction. So let's go ahead and look at the lithium aluminum hydride in ether. Now, this one is going to be so powerful that it can actually reduce carboxylic acids. This is because it's so powerful. It's a much, much more powerful reducing agent, and so it'll go all the way to reducing this to a carboxylic acid, all the way to the primary alcohol. This one can. And again, that's because the hydrides are bonded to metals, right? So it has the electron source readily available here in the form of these metals. Let's go and look at the exact reaction specific details here. So the first thing that actually happens here is that this aluminum actually is going to pull the electrons on the carboxylic acid onto a bond with it, and the hydride is then going to react with the hydrogen here. This will actually leave this aluminum here bonded to this oxygen. And so we'll get this species right here. Now, this is actually going to help make this a better leaving group because it now has this pretty high positive charge attached to it. And so what's going to happen then is your next hydride is going to be able to attack here because your electron density is being pulled over and kept from getting involved in this carboxylic acid as much. And so you're going to get the hydride from another lithium aluminum hydride attacking that carbonyl carbon. That's going to go up the same as it did before. It will make something that's the tetrahedral intermediate again, right? That will come back down. This is going to be a better leaving group because it's bonded to that aluminum there, that metal. And so that's going to be able to leave. Once that leaves, you're left with the carbonyl, aren't you? And so you just do the exact same reaction pathway as we talked about before. We attack the carbonyl with the hydride here. Then we do our acid workup to get the alcohol. Okay. Did I lose anybody there? Huh? See, the big difference here is the presence of that, essentially what would be a complex, right? We have the metal complex here, and this is going to make this a much better leaving group. Okay? That's your big difference here, is the presence of that highly charged metal there to do this with. Whereas the other one just has boron, and that isn't as much of a difference in electronegativity. So it doesn't give the highly charged metal complex to help you. Okay, so let's talk about the reduction of an amide. So this right here is an amide, of course. It's the nitrogen, the amine, next to the carbonyl, right? It's another carboxylic acid derivative. We don't really care about these carbons here. They're R groups. It doesn't matter. Don't get confused about them, okay? I know there's extra functional groups here. People sometimes have a tendency to like zoom in on. They don't matter, okay? So your lithium aluminum hydride is actually powerful enough of a reducing agent that it can actually target amides, okay? And it will react amides away. So again, the sodium borohydride can't reduce an amide. It's not a strong enough reducing agent. The lithium aluminum hydride, on the other hand, very much can reduce an amide and will actually reduce it down. So it's a amine, whatever level of amine would normally be. Hey there. I have really populated. Everybody that was late, by the way, don't forget to talk to me at the end and I'll snap you. I thought I was going to have nobody. We actually did real good, didn't we? Okay. So again, it's the same sort of reaction mechanism as we looked at before, except in this case, it's going to actually go after the negatively charged carbonyl once it goes up to the oxide. And so the first step that's going to happen is this hydride is going to attack the carbonyl carbon here. Normally, when it gets to this step with a normal hydride, it just doesn't have anywhere to go. And so when the electrons come back on, the hydride ends up coming off because it doesn't have any energetic favorability to go the other way. Okay? But in this case, what we're going to end up making is the oxide, and that's going to actually attack this aluminum here, because you're going to have this negative charge right next to that positive charge, right? And aluminum's far enough on the metals that it can actually make a covalent bond, okay? It's a little bit unusual for the metals. We've talked a little bit around that. Some metals can make covalent bonds. Somewhat unusual for metals. This is, again, that tetrahedral intermediate that has a pretty good leaving group here in the form of this aluminum hydroxide. And so this group can actually leave. This is going to pull the electrons in this lone pair on the nitrogen into a bond. This is actually going to help stabilize this. That's part of that stabilization that can happen here, is the lone pair giving a positive charge on the nitrogen here. So the next part is you got your electrophile elimination, which is this group leaving, of course, giving you the double bond here. This is, again, going to be positively charged. This is the iminium ion. Notice it looks like an imide, right? With a double bond to the nitrogen. However, it's positively charged. This is going to make this quite reactive, and so your hydride is going to attack that carbonyl again. That's going to allow your electrons to go back onto this nitrogen. Notice that actually gives you a very low energy comparison wise. This is actually why that nitrogen ends up staying. Anybody have any questions so far? It looks particularly confused or anything. That's good. Okay. It's a little different, but as long as you remember that you can pull lone pairs over to stabilize charges, this should be fairly easy to remember. Okay? That's the sort of difference here, is that normally you would have left with a carbocation, right? But this lone pair can get pulled over to stabilize it. Okay? Okay. All right. Let's go to the next one. So there are times that may be advantageous to stop at your aldehyde. Two specialized reducing agents are going to be lithium tritert butoxy aluminum hydride. This is LTBA, and diisobutyl aluminum hydride. This is DIBAH. Both of these actually have aluminum hydride bonds. And so the hydride anion sources, they're very similar to lithium aluminum hydride. But what you'll notice is they don't have that extra metal, right, the lithium. So they don't quite have the electron availability of the other. They actually have some pretty bulky groups here in comparison to that lithium aluminum hydride, right? And so what will end up happening is, instead of going all the way to the primary alcohol, you're going to end up actually stopping at the aldehyde. And again, that has to do with the bulkiness. We'll go ahead and see a mechanism in just a second. So this right here is that same reaction we've been looking at before. Before we had used lithium aluminum hydride, though. Now we're going to be using the tert-butyl one. This is the different ways you can note this, by the way. So OTBU, tert-butyl. Okay. Tert-butyl, right? TB. Both different ways you can represent this compound right here. Okay. It's another hydride source, but this one is highly sterically hindered, right? We have a lot of pretty bulky groups around it. Okay. This is DIBA over here, by the way. They're going to basically do the exact same things for you. You're not going to have to worry too much about the difference. So we'll get basically the same mechanisms out of these. All right, so the first thing that's going to happen is you're going to get your hydride from your hydride source, of course. And that's going to attack the carbonyl carbon. It's going to form the tetrahedral intermediate, and your leaving group leaves, right? And everybody's familiar with that part right there. But the next step is going to be where the big difference ends up happening. So that reaction is actually going to stop at this aldehyde, because when you try to do the second addition of that hydride, that ends up being much slower than the first addition. And again, that has to do with the bulkiness here. This ends up being a very slow reaction. So let's talk about some of the reasonings for this, okay? So the two major reasons why your reduction from your tritert butoxy aluminum hydride is slower than the lithium aluminum hydride that you'd been using before, we'd been talking about before. Remember, that was the really, really good hydride source, the powerful reducing agent that reduced everything, right? One is going to, of course, be the bulkiness, which I already implicated before. And so what's going to end up happening is you're going to be introducing significant steric hindrances to the nucleophilic addition step. So this right here would be slower, but this next one right here ends up being even slower. So the other part of this is the reaction is going to be carried out in very cold temperatures, typically around negative 75 degrees Celsius, which also slows down the reaction. And so what you're essentially using here, okay, is that by reducing the temperature and increasing the energy barrier, you can selectively make it so the majority of your molecules can't jump over that energy barrier on one part of the reaction, okay? And that's essentially what we've done, right? We had an energy barrier that's slightly higher on one, and so when we try to jump over that next one, we can't make it, can we? And we block the reaction there, okay? It's making sense? So notice it's a very similar concept to what we were talking about before with the cliff face, right? And we have an energy barrier that's higher in one direction than the other. And so we get an irreversible reaction. But instead of it being the same energy barrier from one direction to the other, we just added another step with a higher energy barrier, right? And so that ends up being a little bit too high to reach at negative 75 degrees Celsius. And so we don't get at least the majority of our product going to the primary alcohol. We'll actually stay at the aldehyde. So at room temperature, your hydride here reduction is not going to be controlled, at least not as much. And what's going to happen is your acid chloride here will actually be reduced twice. We'll go all the way down to the primary alcohol because it's going to be too warm. We'll end up being able to overcome both energy barriers without significant difficulties. Okay. So let's go ahead and look at this reaction in a little more detail here. So this would actually be the mechanism for an ester in this case. And so you notice it's the same sort of mechanism as we looked before, right? So again, we attack with that hydride again, and that's going to give us the tetrahedral intermediate. But in this case, we'll have the positive aluminum next to it, so it's going to come over and attack that. Okay? And that's going to then stabilize that tetrahedral intermediate here. Now, at negative 78 degrees Celsius, this is actually going to be stable until you get an acid in here. So if you stay at negative 78 degrees Celsius, this will actually stay stabilized and just stay there like that. You won't have enough energy to do the next step, which is the leaving step, because that would have created a cation, right? So that would be a high energy step again. So you end up stabilizing this tetrahedral intermediate. It's more stable than it normally would be because, again, it has that aluminum there, right? To stabilize the charge, okay? And it's a big, bulky group, so it takes a bit to move. All right, so if you stabilize this and you just make all this and build it up, then whenever you do your acid addition, you're going to get rid of all the rest of the hydride, right? Because that goes off as hydrogen gas. Goodbye. And then you're going to work this up into the alcohol, aren't you? Immediately. Okay? And so what would end up happening is you'd get the alcohol here. However, you'll notice that this right here is a hemiacetal, isn't it? Okay? And so under acidic conditions in water, hemiacetyls are very susceptible to losing their that OH group right there and going to the aldehyde. And so we're just using that next step, being a hemiacetal, as a advantage, if you will, as long as you want to go to the aldehyde, I guess, to go to the aldehyde instead. Everybody see this is actually just a combination of the reactions we've been talking about today and last time, and then the reactions we talked about the week before, right? Ooh, ah. No. Okay. Does anybody have any questions? Fantastic. All right, so let's talk a bit about this stability of this intermediate here. So the relative stability of your tetrahedral intermediate here can actually be rationalized in part by the charge stability of this thing, because and the elimination of the alkoxy group actually generates 2 additional charges here. So if this next step were to go through, we would actually get a negative and a positive charge, right? Which is actually a less stable structure than the other option. So neither of these groups can leave without generating something high energy. This would be sort of the minimum of the high energies, but it's still very high energy. And so as long as you stay below a certain threshold for the energy, as it turns out about negative 78 degrees Celsius, you're not going to have enough kinetic energy to actually make the transition to this. Even if these final products would go away right away. I mean, these would react with stuff around them right away, right? But we just don't have enough energy to get here. Okay? Because this is actually a very high energy intermediate. Isn't that neat? You gotta appreciate that. Just set up such a high energy break apart that it can't undergo. It can't actually go. Okay. This right here is going to be some more organic metallic reagents, of course. We have our lithium alkyl groups. They're very similar in effect to the hydride anions. They're just going to be the alkyl version of this. You'll notice right here is the Grignard reagent that we no one loves so much, right? No? Man, you guys should be so familiar with this. It's ridiculous. I think I started introducing these to you, like halfway through last semester. Grignard reagent, yay. Anyways, again, note that it's a metal bonded to your carbon, right? And so, in effect, it's a carbanion source of various different strengths, right? The Grignards are typically not quite as effective. The lithium are quite effective. So in this case, we're going to get a very similar reaction. We're going to, again, have that carbanion, a very similar reaction to the hydride, right? Just in this case, we're going to add CH3s instead of the hydrogens, right? And so you'll get an attack here. You'll get the leaving group, of course, and then you'll get another attack, okay? And then you'll have to do some sort of acid workup to get your final alcohol right here. Note the Grignard reagent, you get essentially the same thing. You do need 2 equivalents of these to get this full reaction. Without the 2 equivalents, you won't be able to go all the way. You'll get a mixture of things, mixture of products. So this one would be from the Grignard right here. Oftentimes when you do these organometallics, because for the most part, it doesn't actually matter what metallic you use. You can actually write them as carbanions. Is everybody okay with that? But I wrote it as a carbanion here. Okay. And so you'll see that essentially it always ends up being the same sort of reaction. The carbanion is again going to attack that carbonyl carbon. The electron pair that's in the double bond is going to move up onto the tetrahedral intermediate alkoxide here. That's going to come back down, cause the leaving group to leave, reestablishing our carbonyl. This is then going to get another attack on the carbonyl. We'll end up with the tetrahedral oxide intermediate. And then the acid workup is going to give you the alcohol right there. It's the same thing, isn't it? Hopefully everybody can just like blur your eyes and exact same thing as the hydrides, right? Okay. What is the sort of big difference here? Does this ever give you a primary alcohol? No, this is never going to give you primary alcohol, right? Because you're always going to be attacking with R groups. That means you're always going to end up getting a tertiary alcohol here. Okay? Okay, so let's go ahead and look at a little bit weaker of a carbanion source. So this is that lithium dialkyl cuprates that we were talking about before. Remember, that's the weaker one, right? That doesn't go all the way with most of these reactions. And so what we're going to see here is this one's actually going to leave you with a ketone because it's not as powerful as a reducing agent, is it? Okay. And so, again, you added one of these alkyl groups here, the leaving group, which is the chloride here, left, and left you with the ketone dentate. Okay. In this case, it's never the aldehyde, it's always the ketone because you're adding R groups, alkyl groups. Let's go ahead and try it out. Everybody go ahead and show how you can carry out this synthesis right here. And give me a synthesis so we can make sure that you understand it. The next exams, by the way, are all going to be multiple choice because I, number one, don't have time on the third exam to grade your guys' stuff. You guys be able to get any results. I probably will not give you the ACS until you take the final. Okay, because I actually need your data from the final and ACS on the CADs. And so I'm going to force you to take both of them as if you need them. Okay. So what will happen is I'll have those, and then I'll turn around and just put those both in on the final day. So after you take the final, I'll put them both in. Your grades. Okay. You just won't know how you did on the ACS until you take the final. So take them both seriously, as if you're life dependent. It's actually the ACS replaces your lowest exam period. So any exam could be the final, could be exam 3, doesn't matter. Yeah. Whatever your worst exam was, get your place. It's way more beneficial to you. That ACS is super helpful. Oh, I've had a number of emails about people that would like to take it not Friday. Actually, I really could use 4 of you to not take it Friday and take it Thursday afternoon, if that works for anybody. Yeah. I actually found out that the key for the newest one that I have more than 24 of is gone. It's missing. Previous professor probably took it. So, yeah. I also don't have the sheet, the official sheet that I could send in to get graded. So they also took that one. So I only have 20 exams, so I need to take it 20 people at a time. So who would like to take it Thursday afternoon? Anytime past 1. So 1 to 4, anytime during that. 2 hours. Fantastic. This Thursday. I'll be going back through the emails that I got. Thursday, anytime between 1 and 4. That'd be perfect. Yeah. Thank you. I think that's 2. All of the rest of them. Yeah. So exam 3, ACS, and the final are all multiple choices now. No drawing. Yeah. The ACS and the final would have always been multiple choice only. I just don't have time with my other classes that I need to deal with to do it. Yeah, you already got 2 tests on drawing, so that's not uncommon anyways. So. Okay, folks, everybody should have their mechanisms now. Let's check it out. Okay, so how in the world do you carry this synthesis out? We have a few options, actually. So one of the ways you can do this is you can undo aldol condensation here. That would give you this right here is the reactant. And then we can do the undo acyl substitution, which would give you this as your reactant. And so that would be, notice that they basically treated this like a straight sort of chain. We don't need to treat it as a ring really for this. So we can break this up here. This is going to wrap back around, attacking one into the other, right? Okay, and so these are the sort of conditions you would have here. So the first step is you take this carboxylic acid, you're going to attack it with an alkyl group, right? So we can have the carbon there. That's later on going to be the CH right here. Okay, so once you have that extra carbon you need in this, what you're going to do is you're going to use a base. This is going to take the alpha hydrogen off, right? And it's going to give you that carbocation. Once you have a carbocation, well, that then can attack the carbonyl, can't it? Everybody say okay? Now, once you have that carbonyl having been attacked by that carbocation, you need one more set of conditions. You need to go ahead and oxidize off that oxygen, don't you? Because you have too many oxygens at that point. See, we have 2 oxygens, we need 1, right? And so we're going to do a oxidizing conditions like sulfuric acid and heat. That would work very well. And that's going to go ahead and drive off this one. Well, really one of them. It doesn't matter which one. This would just give you symmetric because they're right next to each other like that. And so that's going to give you the elimination. That will give you the double bond. Once you establish the double bond, this is going to be a resonance structure. You're going to have a conjugated system here, aren't you? And so then this becomes much harder to attack. Okay? Okay? Everybody, did I confuse anybody here? I don't have the actual mechanism, but this is the retrosynthesis here. Yeah, I don't typically do a full mechanism for like a synthetic pathway because you can actually do these what's called click chemistry, where you just know what sort of product comes out of each set, and so you can click them together kind of like a Lego set. Makes life easy. Mm-hmm. Yep. Yeah. It's a resonance stabilized carbocation, and that will be the one that'll attack. Right there. So you got an intramolecular addition, then elimination. So this last part is actually very similar to the beginning of this chapter. That's where that actually comes from. This one's from the end of the chapter, actually. So we're going backwards. So that's the one I just showed you, right? And then this is the one from the beginning. I know. We went backwards in the chapter, don't we? Nice symmetry. That's actually it. That's the chapter. That is the semester. That is everything. We are done. You can cry now.